Right, there we go. Okay, we are live, and it is my distinct pleasure today to introduce Dr. Anders Sandberg of the Future of Humanity Institute here at Oxford. Anders is I would like to say, an old friend of mine at this point, and also a quite wonderful human being who bills himself as an academic jack of all trades, which I think is probably the fairest way to sum up what you do. So just sort of kick off with, Anders, what are you working on at the moment? What's keeping you interested?
Wow, everything. So, what my official project is about uncertainty about choices of emerging technology. So, I'm thinking about how we might select the right technologies and avoid the bad ones, and how to handle things like dangerous information. But what's really keeping me obsessed is, of course, writing a book about what I call grand futures. Uh, if we survive and get our act together, which might be a big maybe, of course, but if we do that, where are the limits? How far can we go? Both in terms of space, but survival in time, and gaining control of the matter and energy, etc. And I'm mostly trying to demonstrate that we can know a few things about this. So it's not just hand waving about, well, maybe we could. I think we can actually do a little bit more science and philosophy on it and be a bit more rigorous about it. And then, of course, there is the usual thing about the biosecurity and governance of complex adaptive systems, and me getting obsessed with beetle colors, etc.
We can see a couple of your beetles behind you there.
Yeah, I'm a dilettante when it comes to collecting beetles, really. I'm just collecting ones that are interesting and show the vast space of possible beetles. They're all variations of the same theme, but you got literally millions of species here. And that's just beetles. Now, when we start thinking about thinking, what humans can achieve, etc., the space of possibilities becomes so much bigger. So I'm rather curious about understanding that. And then, of course, one can expand the thinking a bit further and say, well, what about other intelligent life in the universe? How different could they be? How weird could they be in their thinking, etc.?
So that brings us on quite nicely to the topic I was hoping to discuss today. Um, Now, in amongst all of your philosophical and scientific wanderings, you've touched several times on the questions of, are we alone in the universe? And if so, what we can do about it, and if not, what we can do about it. So to kind of frame the discussion a little bit, uh, what is the Drake equation, the Fermi paradox, and what do they tell us about uh, that very critical question of whether we are, you know, on our own here?
So, to take things in historical order, so Fermi's paradox is not really Fermi's and it's not really a paradox, but the story usually told is that in the 50s at the Los Alamos Center, Fermi and the other physicists involved in the Manhattan Project were having lunch, and they were talking a bit about the possibility of traveling to the stars. This was the optimistic 50s, and these were the people who had built the atomic bomb. So they were fairly confident that, of course, we can build rockets that can do that eventually. And they're also talking about the possibility of intelligent life because of a cartoon in the New Yorker about maybe it's little green men from Mars stealing the waste baskets of Central Park. And then Fermi suddenly asked, where is everybody? And that's a really good question because if the universe is enormously big and there's a lot of places where intelligence could have emerged, and it could spread or at least make a very visible fuss about itself, shouldn't we have noticed a lot of aliens by now? So something here is not right. And that's why that tension is why people like to call it a paradox. Now, it's not strictly a logical paradox, it just shows that something in our thinking here doesn't work right. But of course, where that problem lies, that leads to a lot of discussion. So 10 years later or so, at the Green Bank, various astronomers were talking about maybe we should try to listen for signals from aliens. Some astronomers felt that's unlikely to ever work. Others felt, no, this is likely. And then they had a bit of a disagreement. And over lunch, Frank Drake came up with this equation to try to get the disagreement into a nicer form. So this is basically just a long set of numbers that you multiply together. So you start out with the rate of new stars that arrive in the Milky Way every year, multiply by what fraction of them have planets, which was definitely not known back then. Then how many habitable planets would you expect among the stars that had planets? What fraction of those would have life? What fraction of the life-bearing planets would develop intelligence? What fraction of those intelligent species would actually get the technology to communicate? And how long would they communicate for? So you get a bunch of numbers you multiply together, and then you get a guesstimate of how many civilizations could be out there that you could talk to. And if you're optimistic and plug in the numbers, you get a fairly big number, and it makes sense to start listening in the skies. If you're a pessimist, on the other hand, some of the numbers are going to be small, and you're going to find out that, nah, we only get about one civilization. That's us. Don't spend time and effort on this. Now, the problem with the Drake equation is, of course, we're not at all certain about these numbers. Number of new stars in the Milky Way was not actually known very well back then, but Carl Sagan and other influential people were making guesses that turned out to be more or less right. We know that. The fraction of stars with planets, actually, it looks like most have that. So that's essentially one. The number of Earth-like planets or habitable planets per solar system, this is something we don't know. People will probably figure it out over the upcoming decades as we get better at exoplanet studies. But you can still quibble a lot here about, well, maybe they could be really weird planets, not at all like Earth, for really weird life, not like us. And then you get to what's the probability of life? Nobody knows. What's the probability of intelligence? Nobody knows. What's the probability of communication? Nobody knows. And how long does an intelligent species last? Whoa, that would be a very important piece of information. Unfortunately, we don't know that either. So some people say, look, this is just nonsense. You're just stuff you don't know. And that way you're just getting nonsense out. Other, like Jill Tarter, said that actually this is a great way of organizing around certainty. I think that is actually the right way of thinking about it. Sorry, I burst into a mini lecture here, but
No,
it's
no,
such
no.
a fun.
That's one of the reasons I love you, Anders, is that every chat with you I get a little information dump about fascinating things. So mini lecturing, it's basically my whole channel. So highly encouraged. Um, so yeah, I think the those last few terms in the equation seem to be the most critical. You know, the probability of, or the number of planets per star, the number of habitable planets per average planet. You know, these are things that we can pretty easily, relatively easily, uh, check empirically by just looking at the wider universe or making reasonable guesses about stellar and planetary formation. And to some degree, they might change things by an order of magnitude or even a few orders of magnitude, but plugging in reasonable numbers gives you still a lot of planets. We can reasonably assume a lot of planets that could possibly support some form of life. So yeah, the real X factor there is how many planets actually give rise to life, and particularly it would give rise to intelligent life, and how long those civilizations last. And that last point is very much the kind of scary one, and the one that your colleague Nick Bostrom has talked about a fair bit in the context of the Great Filter, which a few people might have
So,
heard
so
of.
it was Robin Hanson, who's
Oh,
associated with our institute, who came up with that term. Incidentally, his little paper about the Great
mm,
Filter is really readable and it's never been submitted to any peer-reviewed journal, and yet he coined a very useful concept and got hundreds of citations. If that had been any normal academic paper, it would have been super successful. Uh, but the important thing about the Great Filter is that we know
mm,
that at least one of the terms in the equation needs to be rather small.
mm.
Otherwise, there should be little green men and aliens everywhere.
We should be picking
And
up on alien TV shows all the time, and although that's sorry to get off track for a little bit. Um, Is it correct in, am I correct in saying that the radio signals that we've sent out with kind of typical television and so forth aren't likely to be getting to any nearby stellar neighbors due to the electromagnetic field of the solar system? Am I making that up, or is that accurate?
Uh, so this has been a point of debate. So the cliche idea is, of course, that all our radio signals are progressing outwards, and the aliens sufficient far away are now getting news about the Berlin Olympics and hearing somebody named Hitler give a speech, and maybe getting the wrong impression of us.
Mm,
But uh, in practice, of course, most radio signals are rather weak, and space is noisy when you deal with radio. So
mm,
there have been a lot of arguments about how close do you need to be to actually get in Earth TV, and many people have been arguing that it doesn't reach more than a few light years. But this is of course based on a particular assumption: how big is your telescope? And most people are doing these arguments or assuming a telescope like the ones we have, like Arecibo in
mm.
Puerto Rico, which is a wonderful entire valley with a big antenna. And in China, they built an even bigger one, essentially using the same trick. These ones are big, and they might be able to catch the television programs for Proxima Centauri, but probably not much further. But there is no reason why you couldn't build bigger telescopes, at least out in space. Also, you have things like the early warning radars from the Cold War. They are kind of beaming out fairly directional signals that might don't contain much information, but they sweep across the sky. And of course, the Arecibo telescope, when it was open, famously sent a message using a narrow beam, which in theory could be received thousands of light years away.
Oh yeah,
Now,
the Arecibo signal. Oh, sorry.
yeah, so the Arecibo signal is kind of a hello universe message. It's a kind of binary sequence that if you organize in the right way, you get a picture. But with, assuming you know exactly what's intended, you can see that, oh, it's a DNA spiral and humans and numbers and the information about the solar system. Except that if you don't know what to look for, you're probably going to just find it mysterious. But it shows that there is some kind of technological species. Now, this was more of a celebration than a serious attempt at communicating because it was aimed at the globular cluster rather far away. And by the time it actually reached that globular cluster, the cluster will actually have moved out of the way. So some people think it's a very stupid idea to deliberately message aliens. So they can be rather calm that this one is not really aimed in any good direction.
So I'm just
Uh,
bringing up the Arecibo message on stream.
mm,
This very blocky, low resolution image of, maybe this is DNA, maybe this is a person, maybe this is the third rock from the sun, these kind of
yeah.
things.
Uh, it's a tricky thing actually to try to construct a message that makes sense,
Mm,
which of course have kept a lot of people very, very busy. So there are these ideas that, well, maybe mathematics is the universal language, so we can use math to bootstrap a message. But going from math to we come in peace is rather hard. So people have spent a lot of effort on this, and it's still somewhat unclear how to do it well. I have my own thinkings about it, mostly about the problems in computer security involved in this.
mm,
But the real issue is if we wanted to be noticed, if we know where somebody might be listening, we could actually beam rather straight at them. The accidental emissions we're doing, they are relatively weak. However, it might be that in a few years we are going to be able to use our telescopes to measure the exoplanet atmospheres and finding what chemicals are in them.
mm,
And if an alien civilization were doing the same with Earth, they might actually notice that there is something odd about this atmosphere because it's full of oxygen, which is fairly unstable because it tends to react with stuff. So something needs to produce that. That's already a hint that there is weird chemistry going on here. And if we're really sensitive, we're going to notice, wait a minute, fluorocarbons. That's really weird molecules to show up. And that's, of course, because our sometimes misguided activities that affect the ozone layer. Um, the funny thing is, there are also other ozone destroying chemicals that actually are being produced by algae in the ocean naturally. There are some brominated hydrocarbons too that naturally destroy a bit of ozone for reasons we don't really know. We don't have any clue why the algae actually produce this stuff. But anyway, you might be able to detect things using optical signals. And indeed, using lasers is probably the best way of transmitting information over long distances because they're not distorted by magnetic fields and radio
Mm.
noise. As we can see the other remote galaxies, we know that they can send light signals rather far away. So there is some chance of detecting aliens rather far away, especially if they're doing stuff on an ambitious scale. The early SETI people, they were of course thinking that the aliens were just like them, under-resourced radio astronomers with a telescope of their size. But later, other astronomers and physicists pointed out that maybe if you wanted to detect intelligent life on Earth, you wouldn't actually look for the deliberate signals, but just the accidental ones. And electromagnetic pulses and the radioactivity from nuclear weapons. The light of cities on the dark side, the fact that objects leave Earth and get into weird orbits, and that many objects on Earth have weird shapes that are not natural. So maybe we should be just looking across the universe for things that don't fit in. If there is an alien super civilization out there, it might be very visible, not because it tries to tell us something, but just because the industrial facilities are so big. So Freeman Dyson, for example, he suggested that a logical conclusion of using more and more energy is that you put solar collectors around the entire star of your solar system, which would show up as a weird infrared emitting object. So maybe we should be looking for things like that.
So,
Now, that is another form of search for extraterrestrial intelligence, and sometimes it's called even Dysonian setting. Now, the big problem is a few decades down the line is we're still rather uncertain about many of the terms in the Drake equation. And that is kind of what led me to my research. We really want to figure out whether the great filter is an early term or a late term. Because if it is that life is super rare, okay, that's kind of cool for us, but it also means that if we get our act together and go to space, our lifespan as a civilization could be very long. But if it's a late term, if life is common, if intelligence is common, then the only explanation for why we're not seeing so much is that, well, either technology is rare or it destroys itself. And that would be very bad news for us. So it's kind of important to figure this one out and then find a way out of the dilemma if that is true. So that's how me and my colleagues at the Institute started thinking about the Fermi Paradox.
so just to show everyone on stream, this is a couple of different versions of a Dyson sphere. Um, so you can kind of just do a ring around the sun, or a whole bunch of individual collectors, or a thick shell around the sun. That one
Which
might not
doesn't
be
work.
possible, right? Yeah.
It's actually a very fun kind of first year physics problem to figure out why a solid shell around the sun actually is not stable. Also, when you calculate the buckling, you can think of it as a tank that is under negative pressure
Mm.
because of the gravity of the sun. You will quickly realize that the material needs to be absurdly strong so it doesn't buckle and implode and bad things happen. So you probably want
Mm.
to have orbiting things or
Mm.
statites, very thin aluminium foil that the light pressure exactly balances the gravity of. So then you can have a kind of bubble around the sun. The cool thing about that bubble is that the total amount of material is not more than
Ooh, ooh,
the
ooh,
mass
just a sec.
gas per test.
Just a sec. We'll get to that in a moment because I definitely want to talk about your ideas of dismantling Mercury, but get to that in a moment. Um, just a quick question from chat. Regarding the possibility of kind of aliens having ever visited Earth, have you got any thoughts on the recently declassified videos from the Pentagon and maybe why they probably haven't visited?
So they are UFO, unidentified flying objects. And the point is, of course, that yeah, they are weird. We don't know what they are. But typically, we see a lot of weird stuff individually that turn out to have very natural explanations. And I think most of them probably have the boring natural explanation or sometimes weird natural explanations. The funny thing is, of course, a lot of people immediately said, "Oh, these Pentagon things, they reveal that they were probably aliens." which is a very weird conclusion to make from we see something we can't explain. It must be aliens. Why couldn't it be fairies or ghosts? And the proper answer is, of course, we filter what we see through our cultural lens. Talking about alien intelligence makes sense, and you can do it in a well-renowned streaming like this one. You can write papers about it. I probably wouldn't have much of an academic career if I started talking too much about ghosts and fairies. But go back 300 or 400 years, and I could probably have a good career here at Oxford University talking about fairies and ghosts back then, as long as I kept to the proper Christian faith, of course. But
Absolutely.
we had this weird cultural idea about what is a reasonable and unreasonable thing to talk about. And the proper rational thing to do is say, okay, that's weird, and we want to figure out what it is, and we might need to do investigation, but we shouldn't jump to conclusions.
Oh, hello.
Hello?
Hello. Ah, there we go. Right. Think
That was
internet issue.
probably the aliens censoring me, but now we know why.
Well,
Yeah.
I think it's the CIA. You know, they know we know too much, and they're coming after us.
Yeah,
Uh,
well, that's the interesting thing. I wonder how many conspiracy theories have been funded by the CIA and other intelligence agencies because it's such a convenient way of muddying the waters. However, as I were told by some very senior people working for with very high security clearance, that yeah, this information it always comes back to bite you. Uh, it sounded very much like they had their own story, and they said that well, some other intelligence agency picks it up and then they give it to your boss and then your boss shows up and says we should investigate this stuff. So it might very well be that we have these weird feedback loops going on where people are making up stories and then forced to check whether their stories they made up are actually true.
Yeah, and there's been some interesting work looking at the impact of the direct impact of kind of cultural phenomena on the reports of, weird things. If you track the development of aliens in films, the kind of representation of, the little grey men with the big heads, or the more earlier sort of reptilian monstrosities, the reported sightings of aliens track with these very, very well. You'll get one film released, and then a whole bunch of the alien sightings over the next 5, 10 years are very directly influenced by that one. Um, and in the case of the recent declassified footage, I've seen some of it, and I'm pretty sure at least one of them is just a an artifact on the lens of the very high resolution hyperspectral zoom camera that fighter jets have. You can sort of see it moving around, and this UFO would be moving at impossibly fast speeds, but it's probably just the little defect on the camera lens that looks a bit weird and that the targeting system has latched onto.
But generally, the world is kind of an interesting place, and a lot of very weird and also very improbable things are happening all the time. Now, the interesting thing is, of course, we're all going around with a lot of very powerful equipment these days. So it's getting harder and harder for any visiting aliens to hide. Even if you say, oh, we're jamming our cameras. Well, jamming is very noticeable. There's a lot of telecom companies that get very upset when that so again, it would tend to show up. Um, so in many ways, the world is full of surveillance, telescopes, and other equipment. So it's getting rather tricky for an alien or a fairy or a ghost to hide. And generally, of course, one way of getting out of the whole Fermi paradox that some people say, oh, it's so hard to travel over interstellar distances, so they're not here. Um, that's one way out of it. So people have been trying to figure out ways of the awkward situation. So one is of course say, oh, we're so primitive we can't detect the signals. If you're an optimist, that there is a lot of aliens out there, or it's so hard to send them or hard to travel, so we don't detect. Now I'm getting much less convinced about these kind of explanation because our telescopes are getting better, and within 1 or 2 centuries we can probably build very big space-based telescopes that can literally read the morning newspapers of the aliens at hundreds or thousands of light years away. So I don't think that works. And in some of my work, I've been arguing that the technology level needed to spam the universe with the robotic spacecraft is not that many decades away from what we can do. So then you need to figure out some other early terms. So one possibility might be, of course, that life is super rare. And this is an interesting one because we actually don't know how easy it is to get life. And
Mm.
if you look at the history of Earth, life arrived rather quickly within the first billion year, perhaps. So you could argue, early life, that means it's probably rather easy. But wait a minute, we are life. We couldn't exist on a planet that developed life in the last million years of its habitability or something like that. You need quite a long time before you get complex life that starts building internet and talking about itself. So what happens is you get this weird observer selection effect. We actually can't use evidence from Earth very much because Earth is a special planet in that it got talkative humans on it. You want to compare that to the rate of life formation of random planets. Unfortunately, we don't have that many random planets to grab. Not even Mars is really a random planet because it's pretty likely that meteors from Mars and Earth have been going back and forth over the past few billion years. And the bacteria spores are pretty hardy, so it's not at all implausible that there could have been life on Mars. And that could have come from Earth. Or Earth life could have come from Mars. If it turns out that there is life under the ice of the moon Europa and around Jupiter on Enceladus, etc., it's not at all implausible that it might be our distant relatives. So maybe life is super rare, but where it arrives, you get a solar system infested.
Mm.
That's one possibility. Another one is life is super easy, but then it immediately runs into a dead end. It's kind of tricky to come up with a good coding system that allow you to copy your genetic code generation from generation. That's not too brittle. So if you change anything, nothing works, or too floppy, so you just get noise taking over. Getting something that's stable enough to produce good organisms, but that can also do evolution. So within a few years, it gets multicellular with nervous systems and start to wonder about the universe. Maybe that's rare. Maybe there are simple codes that just produce rather boring bacteria that keep on being boring bacteria until their sun turns into a red giant. We might be in a universe that's crammed with life. It's just that it's very dumb life.
Yeah, I'm personally somewhat skeptical that the Great Filter is early on, mainly because we've observed, or at least we've done quite a few experiments involving looking at the formation of lipid bilayers and of early protomolecules, organic molecules that could give rise to life. And we've also got there are some interesting theories. I wouldn't say we have any strong evidence, but some interesting theories around hypotheses, really, around the possibility of competing replicators, competing replication systems. So there might have been, some life that was purely RNA based, some life that used an analogous system, but in a somewhat different way. Um, I would suspect there's if it is energetically favorable and plausible for biomolecules and replicating biomolecules to start arising, I would, my intuition at least, is that it would propagate reasonably reliably. Though I think that's something that I would like to see a lot more investigation of. There are a few classic experiments, but there hasn't been a huge amount of work looking into this, I think, quite fundamental issue of how does non-living matter give rise to living matter. And as you say, it's a
And yeah, and there are some really big problems in our understanding here. So getting biomolecules seems to be relatively easy. You find it all over the universe, actually. Getting kind of complex organic molecules, the reddish color of the outer moons and dwarf planets like Pluto, that's actually methane that's been hit by cosmic rays, turning into complex hydrocarbons.
I
The
didn't know
haze
that.
of
That's very
Titan is
interesting.
full of organic molecules. It's a There is plenty of that kind of stuff out there. And you can imagine raining down on the young Earth. The real problem is when you want to go from that kind of stuff to complex polymers, which is really what you need for a genetic
Mm.
code and for an enzyme. This is a point where quite a lot of people actually skip over. And actually, this is where creationists actually quite rightly point out, wait a minute, why are you skipping over that part? Uh, because it's actually really tricky. If you take a random protein and just put it in water, it will actually tend to hydrolyze. It falls apart.
Yeah.
Proteins on their own need to be a bit protected and recycled to stay together. Same thing for DNA and RNA. So one idea that people had is, well, maybe you could have a puddle with biomolecules. It kind of dries out, things polymerize, then some waves slosh in, and you get more molecules. They react a bit, that dries out. So you get a very special environment that does this. It could also be a brine pocket in ice near the pole, or little chambers inside the dark smokers at the bottom of the ocean. There are quite a lot of interesting environments that could do this, but they are much smaller than an entire ocean. Suddenly, it's a tiny, tiny thimble rather than an ocean where maybe the origin takes place. So, working out all of these steps is a super interesting scientific endeavor, and I think abiogenesis is one of the kind of great problems to work on today. But the problem is, it gives us an enormous uncertainty here on probability. And when you look at when people talk about the Drake equation, you see some people assuming, yeah, life, maybe one chance in 10. I don't know, but I admit that it's one chance in 10. Others will say, no, it's rare, one in a million. And then you have a few who actually go all out, saying, no, no, 10 to the minus 16. Very few people want to use even lower numbers because at that point they start to sound like the creationists, and nobody in academia wants to sound like a creationist. But you could make arguments for that, but maybe you need a ridiculously unlikely combination to produce something self-replicating. I don't believe that's true, but we have a huge range of uncertainty. And that is actually at the core of the paper I wrote about it, because when you start plugging in numbers in the Drake equation and you admit that you're making up numbers, typically people then come up with a number at the end and say, okay, I admit I made up these numbers to be illustrative, but here is my guesstimate. And I admit I'm uncertain. But they do it all wrong, because when you're uncertain about something, you actually need to say how uncertain you are. And quite a lot of these examples happen when people don't really estimate the range of uncertainty. So that's what we did.
I'm just pointing down to got your paper on screen, Dissolving the Fermi
Yes.
Paradox, along with Eric Drexler and Toby Ord, both also fascinating people who I'd love to chat to
And Eric
sometime.
wrote this really interesting appendix, which is also worth
Mm.
reading, just about different ways you could organize the emergence of life. He has a lot of really cool ideas there about the
Very
early
cool.
biochemistry.
Well, of course, for those of you who don't know, Eric Drexler is a pioneer of nanotechnology who was among the first to kind of properly lay out a roadmap for nanoscale machines that could build theoretically just about anything from the bottom up. He's done some great work and is clearly a good person to be talking about on this, given that given his in-depth knowledge of chemical engineering and sort of basic physical chemistry.
He also has another interesting paper where he looks at how you can get replication without having a genetic code.
Oh,
Normally, when we think about self-replication, we assume that you have something that needs to have a little blueprint for itself, and then it goes off and makes a copy of itself and inserts a copy of its blueprint. And this is, of course, really complex and hard. But it turns out that if you have gunk, something soft and squishy, like those fallings in the outer solar system or the tar-like chemicals you quite easily get when you just have random chemical reactions, you can make an imprint of a molecule that creates literally a hollow that's shaped like that molecule. And then that can actually catalyze the formation of that molecule. This sounds totally outrageous and crazy, but it actually works in plastics to make plastic that actually acts as a
yeah.
catalyst. And this might be one way early life actually got help getting going. It had clays and gunk of various
Mm.
kinds, and some of that helped copy stuff.
That's a very cool idea because I've heard of the kind of the clay generation, the baseline of that hypothesis. You know, the idea that you get complex clays and they catalyze reactions and so forth. But the idea that it's a physical replication process like that, that's very cool. I'll need to read that.
Yeah, it's definitely worth thinking about, and I think somebody needs to do a PhD about gunk. I think as a category, it's a really interesting one. So in many ways, we have, of course, physics and chemistry of disordered matter, but usually that's clean disordered. It's one kind of molecule rather than the kind of stuff you get behind the stove, the kind of stuff you get in that reagent tube in your chemistry lab that you've been using a little bit too much and have to clean very carefully. That kind of stuff that probably fills the surface of Titan. Um, Indeed, the leachate from landfills is full of things like fulvic acid. And when you look at the molecular structure, it's basically every individual fulvic molecule is different. It's a little Frankenstein collage of other random organic molecules kind of randomly stuck together. And this kind of really random matter has a lot of properties that are worth understanding. And of course, very few people look at it because it's gunk. It's messy, it's annoying, and mostly we treat it like dirt. But it's probably quite an important form of dirt in the universe.
It's something that I think biologists probably delve into a bit more than most people, or at least in sort of neuroscience. The gunk that arises during neurodegeneration disorders and aging, of course, is hugely important in its exact properties, despite being a mess of god awful biomolecules that clog up everything, is really important because it determines, you know, how our cells die and progress in older age, and yeah, how
Uh,
horrible
and
disorders
it's
arise.
interesting because there might be benign and dangerous gunk.
Mm.
So the plaques in Alzheimer's, the amyloid protein, seems to be a particular form of gunk that's kind of almost crystalline. It's a particular protein and it tends to form these very rigid, strong structures. Then you have the age pigment, which seems to be more general gunk, and they don't seem to be good for you, but they don't seem to be as actively bad as the Alzheimer plaque. And they're probably totally benign gunk that is just cosmetically ugly that shows up in our biology that we don't really notice very much because it never turns into something you end up in the hospital for.
Mm.
We really need to understand this better.
And there's some instances of it, like it was. There's still quite a lot of debate over the role of you know, tau protein tangles in degeneration, whether it's the degree to which it's an epiphenomenon that, you know, can characterize the disease but uh, doesn't necessarily cause any problematic function itself, or whether it's the main cause. And I'm a few years out of date on all of that, so I couldn't make any smart pronouncements. But yeah, I think just the fact that a tangle of weird biomolecules looks like bad gunk doesn't necessarily mean it is. So, you know,
Yeah. And gunk is interesting also because it's very, very flexible. It can change shape, maybe act as a catalyst. It reacts to its environment. So I wonder if there is something one can say in general about a theory of gunk. This is
mm,
getting off the track, but I do think somebody needs to write a PhD or become a professor of gunk. I think we might actually find some very valuable things there.
yeah, absolutely. I really like that concept. But yeah, to bring it a bit back to the kind of original focus. Um,
So, uncertainty. So, the real
mm,
problem here is that many of the terms in the Drake equation, we know we're uncertain about it, but most people just throw in one number. Statisticians would say that's a point estimate. And then you multiply together the point estimates and you get another point estimate. But that doesn't tell you how broad the range it could be. And when you start thinking about how big the uncertainty range are for some of the parameters in the Drake equation, some of them are not that uncertain. Star formation, we know that within an order of magnitude, it's on the about a handful of stars per year. Number of planets per star, okay, that's a bit more uncertain, but we still have a guess of it. Life probability. You can make good arguments that the probability is almost one. You can make good arguments that it's one in Google. Uh, Basically, you have 100 orders of magnitude of uncertainty here. And that's the just that parameter. Then you have intelligence, where you can again make an argument that we have 100 orders of magnitude of uncertainty. This is kind of our current state of knowledge. The real answer is somewhere in that interval, probably. And of course, some of us might be optimists and think that no, as soon as you get real life, it tends to evolve into something complex like cats. But others might disagree. And even if I'm optimistic, I must admit I have this huge range. Now, the fun thing is, of course, if I multiply a bunch of uncertain numbers together, I get a distribution of uncertainty in an answer. And the median things I multiply together might actually be very skewed compared to where the full distribution is. So what I did in the paper was I both took what everybody had been saying in various papers, and I took my estimates of what we found in the literature that we think is the actual scientific uncertainty. And in both cases, you find it skewed, but most people writing about it are super optimistic. The median guesstimate is a fair number of civilization. But then you end up with this tail of probability, with quite a lot of probability mass at the very negative end, towards very, very few aliens around.
So I've
So,
just brought up these figures. The little red line here is where we would expect to find ourselves alone in the galaxy, and the blue line is where we would expect to find ourselves alone in the observable universe, i.e., all of the universe that we can theoretically access. And yeah, as you're saying, a lot of the probability falls to the left of those two lines. Um, Indeed, well, please continue.
mm. So the funny thing is that our caricature of the current scientific understanding, if you make the medians very optimistic, you can end up saying, oh, we expect on average there to be 1 million civilizations in the Milky Way. But the median answer in the same probability distribution is 100, which is much more moderate. But you end up still with about one chance in three that you're alone in the observable universe. So in some sense, this answer can make both pessimists and optimists all agree. In another sense, of course, nobody really likes this, because in science we generally try to reduce uncertainty, and this is true in most life. We don't really like to be super uncertain about things. We want to have a bit of a sense of what's actually going on. But sadly, this is the state of knowledge we currently have. Now, it means, of course, that we should go and try to figure out ways of reducing that uncertainty. And there are ways we can observe other planets. If we start seeing signs of life, then the uncertainty about life probability goes down a lot. If we find the wreckage of alien spacecraft, bingo, uncertainty about intelligence goes down a lot. So there are possibilities of getting there. But right now, we actually have this situation where the Fermi paradox is not that surprising. An empty sky is kind of, well, one chance in three.
Yeah, personally, I've found it very convincing, and I think it's a very plausible outcome. But there is a sort of probability on the other end. So you've got the probability of life occurring, probability of intelligent life occurring, and then the amount of time that life is kind of observable for, the amount of time it's sending out radio signals or constructing mega projects or whatnot. And there's a possible explanation for why we might not observe, or there are probably several, but the one I'd like to talk about a bit is estivation. So,
Mhm.
if you could explain to the viewers what that is and why it's plausible.
Well, the question is if it is plausible. I came up with the paper and the term, but I'm still not that convinced that this is what's actually going on. However, it might be something we might want to consider as an intelligent species ourselves. So the basic problem with explanation saying that all civilizations go off and become invisible because they have a technological singularity and become some server farm hidden inside some planet running some kind of alien world of Warcraft forever or something like that, uh, is of course that requires every civilization to want to do it. That's a very tricky sociological claim. But I found one reason why advanced civilization might actually become very quiet, and that is that it's too hot to do much computation right now. So most of what we do as a civilization deep down is dependent on computation. When we talk, well, this is a form of communication and computation. When we do business, that's a form of computation. The market is in some sense acting as a distributed computation, and we are certainly trying to figure out what the best price is, and the ad agencies are trying to figure out the right ad to send to us. When we fall in love, yeah, maybe the qualia, the inherent motion, is actually not information, but we certainly need to know who we're in love with, and so on. So computation really underlies everything we do as an intelligent species, which means that if we expand as a civilization, we want to do a lot of computation. But the problem is, of course, computation actually costs you something. The laws of thermodynamics says that entropy should always increase. And the problem is, if I do a computation, I quite often erase information. That means I'm taking something uncertain, a bit that could be 0, 1, and turn it into something certain, 0. That means that entropy has been reduced. At this point, Maxwell's demon from the thought experiment in thermodynamics shows up and says, "You better pay up, sir. I can't breach the laws of thermodynamics. I need to pay something. I need to hand over a little bit of energy or negentropy to the demon." Basically, that erased bit, that information needs to be turned into waste heat or transported away somehow.
So
So,
if we were thinking about it in the context of a computer, you know, if I want to play a video game, that's all computation. The bits need to be flipped back and forth, and yet the electricity for that, the power to drive it, needs to come from somewhere. We need to, you know, burn coal or you know whatever. Um, but we need to gather the energy in currently in an inefficient way. Is that kind of
yeah, but the reason our computers and phones are running hot today is not really Maxwell's demon forcing us. It's that we have fairly inefficient microchips.
well, yeah,
Uh, and the thing is, of course, we're trying to make them more efficient for all sorts of reasons. Eventually, though, we reach this limit. It's called the Landauer limit. And there is a fair bit of complicated arguments about it. And there is indeed a rebuttal paper taking me and my co authors to task for our interpretation of this. So there is a debate to be had exactly what form of limit it is. But I think it's kind of a practical thing to say that if you want to erase information, you need to pay Maxwell's demon something. It doesn't necessarily have to be energy. If you have empty computer memory, you can actually use zeros from that computer memory and swap your random information into the memory, but eventually you will run out of that memory. So the problem is we have to pay for a computation. And this is generally temperature dependent. If I have a colder computer, then I can run more efficiently. I need to pay less energy to max schema. This is actually a root of the argument I have with Bennett and others, because they would point out that computer memory is actually temperature independent. If you just swap bits for fresh bits, then it's independent of temperature, which is true, but computer memories need to be made.
mm.
And that means taking matter at normal temperature and turning that into something that is containing a lot of zeros. And suddenly Maxwell's demon shows up and wants to be paid again. So what happens is basically that if you have a super civilization that is doing a lot of information processing, eventually you are going to run out of energy and you have to stop. Very sad. And because of the accelerating expansion of the universe, you can only grab hold of a finite amount of stuff before the remote galaxy disappears beyond your horizon. So that means that you have a finite future. And this is, of course, a problem, except that if you could run your computations in a much colder environment, you could get much more computation. So the cost is proportional to temperature. And right now, the emptiness between galaxies is 3 degrees above absolute zero. Well, 2.7 right now. And the good news is it's going down. Because of the expansion of the universe, the background radiation gets redshifted. So basically, it gets divided by the size increase of the universe. So if you wait long enough, it's going down quite a bit. And accelerating expansion, that actually means it's going down exponentially. So this sounds like if I have 1 unit of energy, its value is going up exponentially. Haha. So this seems to suggest that I should just wait. It's a bit like the marshmallow experiment. I can get one marshmallow now, but if I wait long enough, I get two. Except in this case, it's going to be a much bigger marshmallow, and the computational marshmallow for my civilization. Now, it turns out that the accelerating expansion actually puts a limit on how cold the universe gets. Beyond a certain point, it stops getting colder because of the horizon radiation, which I honestly don't know how to explain at all. You need to get some good theoretical physicists in on the show to explain that. But basically, I can get a factor of 10 to the 30 improvement in computation by waiting 2 trillion years.
That's
Now,
a million, 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 I believe.
10 to the 12, yep, yep. So that is a lot of time. Now, actually, you probably want to wait a little bit more than that because the red dwarf stars around are still glowing at that point. So some of them are still going to heat things up. But if you wait maybe 20 trillion years, then they have gone out too, and the universe is dark and quiet, and now you can really run your computer. Now, this is a reason why maybe a super civilization might want to actually say, it's too hot to work right now. We're going to just sleep in this hot early summer of the universe until the coolness of autumn sets in, and then we can do serious stuff. So that's why I call it the estivation hypothesis. So estivation is when an animal sleeps through summer because it's too hot and dry. Hibernation is the counterpart when you sleep through winter because it's too cold. In this case, it's rational for civilizations that mainly care about stuff that's dependent on computation to wait because they get 10 to the 30 times more of what they care about if they just wait. So you can imagine a normal civilization waking up from prehistory, becoming technological, having the advanced civilization, building their spheres, doing the stuff young civilizations do. And then as they mature, they see it all in the material universe. If you've seen one galactic supercluster, you've seen them all. They're not that different. Yeah, you built your Dyson spheres, but most of the really interesting stuff is cultural. It's the books you have written, it's the computer games, it's the mathematical theorems, it's the love affairs and soap operas, and whatever the alien counterparts are. So at that point, you actually might not care too much about the outside physical universe. You care about the internal information-based world. And at this point, it sounds very tempting to skip 20 trillion years into the future, and then you got basically 10 to the 30 times more. You become so much richer. So you might go to sleep, you put some robots in charge of stuff so it doesn't break, and then you have an alarm clock set for rather late in the history of the universe. So that's the idea. Now, could this be used to explain the Fermi paradox? It's kind of neat because it explains why we don't see any advanced super civilizations. It doesn't make that much sense to take all the stars in a galaxy and surround them with isospheres to run your computation because you get so much more by just waiting. You still need to do a few things. You need to make sure, of course, that nobody comes and breaks into your sleeping wall.
Do
So
not disturb for the next quadrillion years signs everywhere.
yes, so we might want to look for them. There are certain activities that you need to stop. For example, if some young civilization evolves in some of your stuff and then start trying to take the stuff, you need to slap them down and stop them. So one of the ways of testing this is, of course, to build self-replicating interstellar settlement probes. You build robots to take over the accessible universe. If somebody or something stops you from doing that, then you know very well that, okay, there are elders out there, they're asleep and they don't like us doing that. If they're nice elders, they tell us beforehand. If they're nasty elders, they blow us up. So we might want to be a bit careful about this possibility. So there is a bunch of aspects of this hypothesis. And one important thing is the matter that you want to use later on. You shouldn't be seeing too much process and losing that. What's the point of kind of going to the far future if most of your stuff has decayed or disappeared out into galactic voids? So in the paper, we suggest that we should be looking at all the weird processes that seem to be stopping the dissipation of matter. And this is the main reason I don't really believe this is the explanation for the empty sky, because there seems to be a fair bit of them. You might imagine that, yeah, the stars are shining and kind of losing energy by fusion, but it's only 0.7% at most of the mass energy of a star that ever gets turned into energy. fusion is actually really, really inefficient. We might be very impressed by the solar power of the sun, but that's just because it's big and produce a lot of power compared to us. In terms of turning matter into energy, it's really inefficient.
Mm.
If you give me a nice massive black hole, I can take the matter from that star and throw it into an accretion disk and collect the energy from that and get up to 42% efficiency of converting the mass into energy. That's way more. So I don't actually need to stop the stars from glowing. Similarly, there might be other processes that lose important matter. For example, supernovas heat up the gas in the galaxy, and you get fountains of hot gas leaving the galactic plane, going out into intergalactic space. Around us, they probably cool down and fall back in as gas clouds, and then lead to this cycle where cold gas clouds come in, lead to new star formation, and it keeps repeating. But in many galactic clusters, you have hot gas that is so hot that it will not fall into galaxy. It might just leak off between the galaxies out into the outer voids and are going to be totally lost. And that might be happening to 90% of the baryonic mass. Meanwhile, the non-baryonic mass, the dark matter, it's very unclear whether that's useful or not. It might be that you can feed it somehow into black holes and get useful energy. It doesn't work with my accretion disk trick at all because that needs to emit electromagnetic radiation to do it. But maybe there is something super civilization know that we don't know yet. It's actually fairly likely that there is. It could be that dark matter is useful. But the result of the paper was we found that it doesn't look like anybody's really seriously managing the universe to keep matter together. That's either a sign that nobody's around or nobody's doing estimation because it's stupid for some reason, or it might be that they actually don't care about having enormous amount of matter. They just need enough matter for some very big projects. They're kind of modest super civilizations, whatever that means. Or it could, of course, be that, yeah, we're actually alone in the universe, but we might, once we have become a galaxy spanning super civilization, got a bit jaded with the material world, decide, okay, let's skip to the cool the late eras and have a really proper super civilization.
Might stop becoming involved and sublime away, leaving just the
Yeah, to
culture
use
to.
Ian Banks' terms. So that's, of course, a common idea that advanced civilizations maybe they become uninterested in the material universe and go somewhere else. And I think partially this is just that we project many standard human religious concepts, which in terms of probably projections of our psychology. As you get older, you have less energy, you might have acquired some wisdom, you realize that a lot of the stupid stuff young people are doing, you did that too, and nobody listens to your advice. They're going to keep repeating it. So you're going to focus on what you think is actually meaningful and important. Then they project that up to that maybe this is what religion is about. Maybe that's why I need to meditate away from. And then maybe we project it on super civilization, imagine them as elders who are wise and go off to some spiritual. Or it might be that they find a way of hacking the simulation that is the universe and get out in the operating system and actually participate in the real world. But it's not clear entirely what this might, how to assign probabilities to this. It seems that there is quite a lot of different pathways you can take as a super civilization. Because normally our imagination is rather limited when thinking about the very far future. So if I want to write a story about the United Kingdom in the year 2030, I'm going to have so much fun. It's going to be so easy. I can think about the various people who I know likely are going to be around. I can make various innovations. I can do a bit of political satire, lots of details. Now, suppose that I'm trying to describe the UK in 100 years' time. I'm going to be much more general. I'm going to be glossing things over. I could, of course, try to make up stories about everyday life and how you try to clean with your nanoswarm or etc. Uh, it might work, but generally people tend to use less and less detail the further away you go from the present. Partially because we're more uncertain, partially because of something called construal theory in psychology. We tend to use these construals when something is remote from us. And we tend to do it in a fairly predictable way. We tend to assume that people far away in space and time were more driven by principles. They're much more like an out group than an in group. So we know that people in our team, they're all individuals and they all got weird reasons for doing what they do. But those other ones, whether they're a different religion or living in a remote country, we tend to assume they're all driven by the culture or their religion. And this is why construal theory shows us that our models of a far future tend to be very sleek. You tend to end up with kind of crystals and togas. Everything is made out of force fields. You rarely get that rich detail. Ian M. Banks in his culture novels was actually fun because he tried to envision even everyday life in a super civilization. But most of us fail at that. Even more importantly, we fail at imagining what they might want to do. Imagine that you're a Stone Age person trying to imagine the far flung year of 2020. Of course, you don't even have numbers for years. That was invented actually just a few thousand years ago and was a revolution. Before that, years were about what happened in that year, who was king at that year. And then the Sassanid Empire, I think it was, started by saying, no, this is year zero. And now we're going to count upwards using integers. And many people literally rebelled against that because that was a horrifying thought. There's an infinite Sassanid Empire because there's an infinite number of numbers. That's so weird. But all history before, since there are no negative numbers, I mean, what could be less than nothing? All history disappeared. They couldn't even imagine that. So our Stone Age ancestors trying to imagine the year 2020 might imagine us having caves and having steak mammoths like everywhere because progress didn't exist. That was invented just a few centuries ago. The idea that the world is actually accumulating knowledge and changing. And generally, if you ask some of my colleagues here at Oxford a few centuries back, their vision of the future would also appear very limited. Again, they couldn't even imagine a globalized world where people have really weird views. And similarly, we of course get into deep trouble when we try to think about the future. This is quite often why you tend to make it very utopian or dystopian because that's at least a way of organizing your thoughts. But if you look at the current world, I don't think it's either utopian or dystopian. Yep, right now many of us are in self-isolation because of a pandemic. Yeah, that's kind of bad. At the same time, we're doing weird tricks on the internet. We're launching rockets. We're solving important problems in machine learning. People are inventing new institutions. Fewer people are poor now than ever in history, and so on and so on. This is not a utopia dystopia that makes sense. It's that weird mixture, and I should expect a super civilization to be just like this, but 10 to the 30 times more. We can't imagine that. But there is so much value at stake in the far future that I think it's worth thinking as hard as we can about what we can do to ensure that we get to a good far future.
I think that's an excellent note to leave it on. I know you've got to go at some point, and though I would adore chatting for the rest of the evening about oh, we still
Always
need
happy to
to.
repeat this about other random topics. There's
Excellent.
so many things under the sun and the other suns worth talking about, whether that is gunk or control theory or how we can use the theories from cybernetics to talk about politics.
Well, the first thing we'll talk about next time will have to be how do we turn Mercury into a harvesting system for all of the sun's energy, or at least a substantial portion of it.
Yeah,
Um,
Mercury, it has it coming. But that's for
uh,
later.
Mappa Mundi in Hereford. I shall look into this afterwards. So yeah, uh, thank you very much, Anders, for coming on. It's been a pleasure, and I will certainly take you up on that offer to have you back on sometime.
Well, the delight was all mine. Have fun. Live long
Thank
and
you.
prosper.
Indeed.
Cheers.
Bye.
Bye bye.
Right. There we go. Right. Oh, I need to. How do I get the video capture box back on? It's not turning on. Right. I'm going to look into this Mappa Mundi thing. Uh, because that sounds. Oh yes, this huge medieval map. Um, yeah, I think that's a particularly interesting example of. Oh, where is it? Can I get a good view of it? Explore now. Is this? Does that let me show it? It's a particularly fascinating example of how utterly different our worldview is. Um, and this is not a very good image. I don't want 3D. I want, oh, do I don't know. I can't bloody see it. But have a have a look at this sometime. Other people. This is Mappa Mundi. Sorry, and just the sheer massive difference between medieval views of the world and modern views of the world, or even post-medieval, just a few centuries ago, before we'd kind of fully mapped out all of the land. The the view, both the cultural and geographical view of how the world fits together, has changed so much that if you tried to explain the internet or modern finance or distribution networks or even like the nation state to people a few thousand years ago, it would have been absolutely baffling. Um, yes, this giant foot people are fucking medieval weird people is like one of my favorite genres of art. Um, Weird medieval people should come up with it. Um, let's see, any of the like. Okay, obviously we've got Snail Man here. We all love Snail Man, obviously. Um, Pooping Tree Guy. Here we go. This is what I'm thinking of. Oh yeah, the India gold thing is interesting because the flow of goods along the Silk Road from the east to the west resulted in all of these bizarre beliefs about how like incredibly wealthy the East was because it was sending these spices and precious metals and so forth. Though of course to some degree were just precious in the West because they were so rare. Um, so it's not that it was incredibly wealthy, but yeah. So these weird medieval people. I think I'm not sure if these are from Mappamundi, but the there's the guy with the foot shading himself from the sun. We've got Torso Face. Torso Face is one of my favourites. I love Torso Face. Uh, this dude's just like, hey man, hey, have you got a head I could borrow? That'd be great. Um, anyway, so yeah, that was lovely having Anders on. He really is an excellent chap, a very good friend, and one of the most fascinating academics I know. Um, he's also one of the happiest people I know, and speaking with him always cheers me up a bit. He's got a very high hedonic baseline, which uh, I I would envy him if it weren't for the fact that he's doing such a good job with it. That I think he really deserves it. Anyway, so I'm gonna end the stream there, but thank you, thank you, Josh, for your commentary and for getting involved. And yeah, I hope people enjoyed that. And I will definitely be bringing him back on because, yeah, he's great. So I hope you all have a lovely Wednesday evening. It's Wednesday today, isn't it? Yeah. Lovely Wednesday evening, or whatever time of day it is. And yeah, as Anders said, live long and prosper. Ta ta.